Welcome to the presentation of paper DAG scheduling and analysis on multiprocessor systems, exploitation of parallelism and dependency. My name is Shuai. I'm a research associate working in University of York. This presentation is organized as follows. We first describe the background of our work, the definition of the DAG task, and the state of art in scheduling and analyzing DAG tasks. We then propose the concurrent provider and the consumer model, which can be used to fully describe the internal dependency and the parallelism between nodes in a DAG. Based on the CPC, we propose a rule-based DAG schedule and response time analysis. We finally present the experimental results and draws the conclusion. With more complex functionalities being implemented in the emerging real-time applications, directed acyclic DAGs are used to model the functional dependencies. The examples include the 5G base stations and the automotive systems. In such applications, the system activities can be effectively modeled as a single recurrent DAG task. So in this work, we focus on a single periodic, non-preemptive DAG task that is running on a homogeneous multiprocessor platform. And we propose novel methods on modeling, scheduling, and analyzing a DAG task with the aim for shorter mix span and tighter analytical bounds. So a DAG task can be defined by a graph containing a set of nodes and edges. A node in a DAG is a computation unit that must be executed in a sequential manner. Each node has a worst-case execution time. An edge connecting two nodes defines the execution dependency. So take this example here. This DAG has 8 nodes, and the number of the top right of each node gives its WCET. And for any two nodes that are connected by an edge, for example, node 5 and 7, node 7 can only start it after node 5 has finished. And for a given node, we have a set of functions that describe the relation between these and other nodes in the DAG. So let's take node 7 as an example. So first, this node has a set of preceding nodes that are connected directly to node 7, which are node 5 and 6. It also has a set of successor nodes that are connected from node 7, which is node 8 in this example. In addition, it has a set of ancestors and descendant nodes that are transitively connected to and from this node. And in this example, the ancestors are node 1, 5, 6, and the descendants are node 8. Lastly, it has a set of nodes that can execute concurrently with node 7, which are node 2, 3, and 4. In addition, a DAG has the following fundamental features. First, a path is a node sequence in a DAG, and its length is given by the sum of the WCETs of all nodes in that path. And we use lambda star to denote the longest path in the DAG, which is termed as the critical path. Nodes in the critical path are called the critical nodes, and the others are the non-critical ones. And each DAG has a length L, which is equals to the critical path, and the workload W, which equals to the WCETs of all nodes in the DAG. And for the same example, we have the critical path with node 1, 5, 7, 8, and the length of the DAG is 10, and its workload is 24. So most of the existing work schedule DAGs based on a work-conserving scheduler, which never idles a call if there exist pending nodes waiting to be executed. And for any work-conserving scheduler, the worst-case finish of a DAG can be effectively bounded by the worst-case finish of its critical path, known as the classic approach. So in this equation, the worst-case finish of the DAG is first given by the length of its critical path plus the interferencing workload from other nodes that are executing across M calls. However, this analysis can be pessimistic if the execution order of the nodes is known before execution. So take the same example here. Based on the equation, we can have the worst case finish of 17. But if we have a explicit execution order, for example, the one shown here, we can have a worst case makespan of 13 instead of 17. So based on the above, we can know that with an explicit order known before, a tighter bound can be obtained. And in this case, a node can only be delayed by its concurrent nodes that are scheduled before the node. So in this analysis, the worst case finish of the DAG is given by the node that finishes latest. And for one node, it can start only after all its procedure nodes has finished, and before its execution, it can incur a interference from all its concurrent nodes that are scheduled before it. So however, this analysis still has certain degree of pessimism because it assumes that each node in the interfering set can actually cause a delay, which is not always true because of the potential parallel execution. So let's take the same example and look at node 6 in this case. With the execution order like this, we can see that node 6 has a worst case finish time of 2. However, with the analysis applied, we have a worst case finish time of 6. As for the scheduling methods, the state-of-the-art method schedules nodes by guaranteeing the critical path first and the early procedure path of the critical path first. So the early procedure path here means the non-critical nodes that are linked to an early critical nodes. However, for the procedure paths with the same earlierness, they are ordered by the length of their complete passes. So let's take this example, and with the scheduling method, the following execution order is, can be obtained. So first, node 1 and 2 are scheduled to execute, followed by 5, 7, and 9. And then node 3 is executed, followed by 6, 8, and 10. So for node 5, 7, 9, and 6, 8, and 10, the order of their lengths can be the exactly opposite to their complete passes. So this cannot maximize the node parallelism and can lead to a prolonged finish time. So based on the above, we can understand that minimizing the delay on the critical path can effectively reduce the makespan of the DAG. So this also implies the critical path first execution. However, this can be very difficult to achieve because the critical path can be delayed multiple times by different non-critical nodes. And the execution order of these nodes can have a direct impact on the delay of the DAG. So to fully exploit node dependency and parallelism, we propose the concurrent provider and the consumer model. So essentially, this model divides the critical path into a set of subpasses. And for each subpass, the CPC model identifies the non-critical nodes that can execute concurrently with the current subpass, as well as impose a direct delay to the start of the next subpass. And the underlying intuition is with the critical subpass executed first in one call, it naturally provides a conceptual capacity on the rest of the calls for the non-critical nodes to execute. And utilizing this capacity to execute, there will be no delay being imposed to the critical path. And for this reason, we term the critical path as the set of capacity providers and the non-critical nodes as the consumers. And for each provider, it can offer certain capacity, which is the length of the provider, for the concurrent consumers to execute in parallel on the remote processors. And here is how the CPC model can be constructed. So starting from the first node in the critical path, a capacity provider is formed by taking the following nodes that cannot be delayed by any of the non-critical nodes. So this also highlights the property that a provider can only incur one delay before their execution. And then for each provider, its consumer nodes are given by the nodes that execute concurrently with the provider, as well as can impose a direct delay to the start of the next provider. So for this example, we can have 4 providers, and each of the first 3 providers has their own consumer nodes. And in addition, there can be certain nodes that are not in a consumer group of a provider, but can still execute concurrently with the provider. So such nodes are denoted as G. So node in G can actually execute concurrently with the consumer nodes of the provider, and this will impose a delay to the finish of the consumers and hence the start of the next provider. So for the same example, we can see that although node 9 and 12 are not in the consumer group of the first provider, but they can still execute in concurrent with them and impose a potential delay. So based on the CPC model, we provide a rule-based scheduling method to minimize the makespan. So the first rule is the provider nodes must execute first. So this is equivalent to the critical path first execution and can provide the maximum capacity for executing other nodes on rest of the course. And the second rule is to always let early consumer groups to execute first. This will minimize the interference of a consumer group F from the nodes in G, which are not in the consumer group, but can execute concurrently with them. So for the same example here, with rule 1 and 2 applied, we will have the execution order that nodes 1 and 2 execute first along with 7 and 8, followed by nodes 3 and 4 along with 9, 10, 11, and lastly node 5 along with 12, 13, and 14. So for the nodes in one consumer group, the objective is to minimize its finish time so that it can have the least delay on the next provider. However, simply applying certain heuristics is not sufficient because each consumer group can actually form a smaller local DAG. So therefore, we apply CPC in a recursive fashion to the consumer groups to form inner CPC models. And the rules 1 and 2 will be applied on each inner CPC model. This process will repeat until all the paths in a consumer group are independent from each other. And then the final rule is applied to the independent paths in the consumer groups in each innermost CPC, where we always let the longer paths in a consumer group to execute first. This maximizes the node level parallelism and minimizes the finish time of the consumer group. So for this example, we have only one consumer group that forms a local DAG. So we apply CPC to construct the inner CPC models until all paths in the consumer group are independent with each other. And then we apply rule 3 to schedule the longer path first. So different from the existing schedule, the proposed methods performs the following. First, it transforms a DAG task into the proposed CPC model. And based on the model, it statically orders the execution of each node. And based on the pre-planned order, it schedules the nodes at runtime. However, step 1 and 2 can be performed offline if the input DAG is known before execution, which effectively reduce its execution cost to that of the traditional fixed priority schedule. With the CBC and the schedule proposed, a new response time analysis is developed to provide tighter bounds than existing methods. So this analysis has two versions. The first version only assumes critical path first and allows any execution order for the non-critical nodes. And the second bound assumes the critical path first, as well as an explicit execution order of the non-critical nodes. So essentially, this analysis computes the worst case finish of a DAG by first bound the workload that can execute in parallel with a provider and apply it as a safe reduction on the delay of the critical path. And second, bounds the actual delay that caused by the interference in workload, which executes after its provider is finished, and use this as the actual delay on the next provider. With the proposed method, we conducted a set of experiments to investigate the effectiveness. The evaluated methods include the proposed analysis with two versions, the proposed scheduling order, the classic analysis for work-conserving schedule, and the state-of-art schedule and the analysis methods. And in particular, we investigate above methods under different number of processors and different level of parallelism of the DAG and the different lengths of the critical path. The first set of the experiments reports the worst case mix span obtained by the classic bound for work conserving schedule, the proposed analysis with critical path first only, the state-of-art analysis with their scheduling applied, and the proposed analysis with the rule-based scheduling applied. So from the results, we can observe that the proposed methods can lead to shorter and more accurate mix span when the number of calls is relatively high, and the critical section is relatively long. And for the analysis with critical path first only, it is more beneficial for DAGs which has a relatively low parallelism. The intuition behind this observation is with the number of calls increase or the length of the critical path increased, it provides more capacity for the non-critical nodes to execute in parallel with the critical path on the rest of calls. So in our analysis, we explicitly account for the workload that execute along with the critical path and then apply it as a reduction to the final delay on the finish of the critical path. So with such parameter scaled, our analysis provides better results. Second set of experiments investigates the effectiveness of the proposed schedule. So at the left side of the table 1, we present the percentage of improvement where the proposed schedule outperforms the state of art. And on the right side, we give the percentage of improvement in which the state of art performs better. And in table 2, we summarize the number of advantage cases obtained by the proposed schedule and the state of art, followed by the scientific significance. So from the results, we can observe that the proposed schedule has a better performance because first, it has a higher percentage and the significance of improvement. And second, it has a higher number of advantage cases. Similar observation can also be obtained for the proposed and existing analysis. So to sum up, in this work, we proposed a concurrent provider and consumer model, which captures node parallelism and dependency and can be applied recursively to fully fresh DAG. And based on the CBC, we propose a rule-based scheduling method that improves the node level parallelism and reduces the mix span of the DAG. In addition, a response time analysis is also developed that fully explores parallel execution in DAG task and tightens the worst case mix span approximation. And in future work, we aim to further optimizing the proposed scheduling methods and to support multiple DAGs with a work-conserving approach. And thank you for your attention.